Today I want to talk about one of the most powerful and precise techniques in modern thin film technology. Imagine creating a mirror that reflects 99.99% of light with almost zero scattering, or a protective coating that withstands extreme laser powers without any damage. That's the level of performance our IBD, that is ion beam deposition, delivers. In our world of advanced materials, starting from smartphone screen to quantum devices, almost everything relies on thin film. That is, that thin film is of just few nanometers to micrometer thickness. That's it. Uh, our conventional methods like thermal evaporation or magnetron sputtering often fall short when we demand the extreme high quality thin films. But our ion beam deposition gives ultra thin layers with extreme dense, smooth, uniform, pure, and perfectly controllable thickness of thin films. So then let's learn about this ion beam deposition. In this video, I'll be covering about ion beam deposition, their types, and detailed explanation of mechanism how this ion beam deposition works, and advantages, disadvantages of ion beam deposition, their applications. So let's start. This ion beam deposition is a part of physical vapor deposition mainly. What is this physical vapor deposition? It's a vacuum based methods where solid materials purely vaporized or condensed on a substrate to form thin films. Unlike our chemical vapor deposition, where we will use chemical reactions to form the thin films, here there is no chemical reactions happening, and it's all physical process like evaporation or sputtering. So when we come to definition of this ion beam deposition, it goes like this. Ion beam deposition is a physical vapor deposition method that uses a controlled beam of energetic ions to either directly sputter the material from a target or to assist and modify the growth of a film being deposited by another source. Now, let's learn about the types of ion beam deposition. In ion beam deposition, there are two types, that is, direct ion beam deposition or ion beam sputtering. One more is ion beam assisted deposition. What is this direct ion beam deposition means? In this, what we will do, we will take external ion beam and will bombard that beam on a target. After that bombardment, the atoms will be sputtered out from the target and they will move towards the substrate to form the thin film. That is one method. In ion beam assisted deposition, we will be using one more ion gun to make that thin film to uh, smoothly spread over all the surface to in all the surface. That's ion beam assisted deposition. Now let's learn in detail how this actually works physically. Okay. First, we will learn about ion beam sputtering deposition. Here, a stream of charged particles, usually positively charged argon ions or other ions, generated in an ion source like a Kaufman ion gun. You can see here, this is the one. These ions are extracted from a plasma, hot ionized gas, and accelerated using electric field to gain kinetic energy. Typically, they carry energies around 500 to 2000 electron volt, which is high enough to cause physical changes, but not so extreme that it destroys the target entirely. The beam is focused using a magnetic or electrostatic lens to make it narrow and precise, like how our laser pointer works. And after these ions travel through the vacuum chamber and collide with the target surface, they can collide on the target surface at any angle based on our preference. And when they collide, each ion acts like a tiny projector here, and they transfer the kinetic energy to the target's atom through elastic collisions. And this all process is purely physical, no chemical reactions are involved here. When these ions, here the ion speed is around 10 to the power 5 to 10 power 6 meter per second, and its mass is almost the same as the mass of the target atoms. So when we are selecting the ion beam, the ion mass and the target atom's mass should be almost similar so that entire kinetic energy can be transferred smoothly to target's atom. Suppose say if the energy of the ion beam is too low, like less than 50 electron volt, nothing much happens. They will directly, like they will just hit it and they will move on. If it is too high, suppose say greater than 10 kilo electron volt, then the ion might implant deep into the target without any sputtering. The ion, after entering the target, it displaces the atom. This displaced atom then collides with the neighboring atoms. Then they will collide with furthermore atoms, and this like starts like a chain reaction. Here you can see incident atom is coming and colliding with the atom, and this atom is moving, and this atom will collide with neighboring atoms, further creating like further disturbing that atom from their lattice side. This spread out is in a roughly spherical or elliptical volume near the surface. It will last only for picoseconds. And when this incident ion comes and hits the target's atom, most of its energy is dissipated as heat, and but some of the energy and is given to the atom. This whole phenomena, how this atom ion will come and hit the atom and how they will displace, all this phenomena is explained by Peter Sigmund, a physicist. He described it in mathematically using the binary collision approximation. That theory is given as Sigmund's theory. You can go to this link which I have mentioned here below, where they will be explaining the Sigmund's theory clearly. Then this chain reaction is what turns one ion's energy into widespread atomic disruption, enabling the efficient materials removal without melting the target. Okay, when an atom gets the energy from the incident ion, it overcomes the binding energy of the surface and they will eject from the target with having energy 1 to 20 electron volt. For an atom from the target to escape, it should have a kinetic energy greater than the binding energy, which depends upon the material which we have taken as a target. So, in this chain reaction, only atoms within the 1 to 2 nanometer of the surface can be ejected. The deeper ones lose too much energy and they will not be reaching the edge of the target. And the atoms which are near to the surface, they will be getting kicked towards the surface with sufficient energy and it will overcome that binding energy and flies out. This after the atoms coming out of the target surface, they travel in high vacuum. I'll show you. This blue lines indicates the atoms coming out of the target surface. They travel in high vacuum where there is no gas molecules, so there is no point of losing the energy by collision. The atoms which are coming out of the target, we are calling them as add atoms. They are the single atoms. They just have landed on the surface of the substrate, and they when they arrive, they don't stay stuck in the same place. They will move around the substrate. Like we are giving, yeah, it's like giving them skates to spread, yeah, evenly on the substrate because they have certain energy to move there, which the energy which is given by the ion beam. So this is how we will form the thin films using our ion beam and deposition, which is direct ion beam deposition method. Next, we will come to ion beam assisted deposition method. Here, the primary steps where we will take the atoms out of the target is same as that we have discussed in our previous type. But extra thing here is we will be using one more ion gun for mixing the thin film formed on the substrate. What we will do here, as the atoms which are coming from the target enters the substrate, the same exact time we will send a separate beam of ions uh, towards the substrate surface. These ions move with energy 22,000 electron volt, which is much faster and stronger than the arriving atoms. They act like tiny hammers, constantly tapping the film as it grows. When an ion hits, it creates small recoil movements. This recoil movement helps the atom to move to empty space. Why it is necessary, I'll show you in the next slide. Here in the first image, you can see uh, this is the atoms coming from target without any extra ion beam for mixing them. In the below image, you can see when we include the extra ion beam to make them fill the vacuum which is being formed here. You can see here, right? This vacuum can be filled when we are using the ion beam for mixing. They will hit these atoms and making them to come down and fill these vacuums which have been formed. And in this right side image, you can see that there is a vacuums created with different temperatures, and with higher temperature, the vacuums are being filled. So with increase in temperature, some temperature, we can without using this ion beam, extra ion beam, we can make those vacuums to be filled evenly. So these are the two types which comes under our ion beam deposition. Next, I'm showing you the images, SEM images of one with Y2O3 in the left, where they have grown thin films on the quartz fiber with various electron beam currents. On the right, you have a cross-sectional view of the thin films, how they have formed evenly. You can see that the spread is so even. That's how precise our ion beam deposition works. Next, we will come to advantages and disadvantages of our ion beam deposition. In When we come to advantages, we can form extremely dense films with very low porosity, and we can have ultra smooth surface, and it has extra excellent adhesion and interface quality. We can control the thickness of the thin film. We can control the stoichiometry. Uh, with we whatever material we get, we will be having high purity and low contamination. We can do this experiment in even in low temperature deposition, for example, using our ion beam assisted deposition method, and we can form the metastable phases as well. It can be used even in optical, electrical, mechanical performance, develop the mechanical performance and as well everything. But there are some disadvantages in this method. It is heavy cost, highly costly, and it is not ideal for large area uniform coating. And deposition rate is so small here. That is some disadvantages of our IBD. Next, when we come to application, uh, here in this application we can have High reflectivity mirrors and AR coatings, we can use it in interference filters as well. And for lasers and photonics, damage resistant coatings for ultra fast high energy lasers and beam splitters. Here and all we can use this thing. And also in semiconductors electronics, the materials formed from this method can be having high dielectric property, and we can form thin film read and write heads, transparent conducting oxides, and can also be formed. Also, it can be used in the resistant coatings and infrared sensor technologies as well. Some of them I have mentioned here, you can go through them. This is all about our ion beam deposition method. I hope this video is being useful for you. Uh, Thank you, everyone.